Hi folks, we're going to take a look at the rest of today's lesson. So in the first part of the lesson, we tried to make some conjectures for some derivative rules that would allow us to find derivatives easily, meaning without having to go through the limit definition of derivative. And we made a bunch of conjectures, and one of the ones we showed was that the derivative of a sum of two functions is the same as adding together the two individual derivatives. All right, and we actually proved that. So now what we're going to do is look at another one of our conjectures, which is that if I'm taking the derivative of the power of x, any power of x, the pattern we seem to see was that the new function, the derivative function, was going to be given by a coefficient which is the same as the original power, so n times x to the, and the new power would just be one less than the original one. Okay, so n times x to the n minus 1. So we can think of taking the derivative of x to the n as you bring down the original exponent, and then the new exponent goes down by 1. So if I was taking the derivative of x to the fourth, it would be 4x to the power 3. All right, and this would be very useful. What was nice is that it also worked when we tried something like x to the 3 halves. Okay, so that implies to us that this rule probably works for any exponent, any real numbered exponent. Okay. However, in terms of trying to prove this, we're going to stick with n being a natural number. So in other words, a positive integer. And you'll see why in our proof we need to do that. It certainly gets more difficult to prove beyond natural numbers, but we'll take that as being true. But we will prove, or at least come close to proving it, for n being a natural number. All right, so if I want to prove this, I basically have to start with one side and show that it's equal to the other side. So I'm going to start with the left-hand side here. So I have the derivative of x to the n. And if I want to prove something, usually I have to go back to the definition of my expression. And the definition of the derivative of x to the n with respect to x is given by that limit definition. So it's the limit as h approaches 0 of the function evaluated at x plus h, so that's just going to be x plus h to the n, minus the function evaluated at x, so x to the n, all over h. All right, and so this is what I'm going to be working with. Now, of course, this is an indeterminate form because both numerator and denominator approach 0, so my hope is that I can do some algebra in the numerator that'll eventually produce a factor of h that I can reduce with the h in the denominator. All right, and this is where we're going to see why we're assuming that n is a positive integer, because I'm going to use the fact that I have a system for expanding binomials. Okay, and I'm referring, of course, to Pascal's triangle. So let's go to the side and remind ourselves how that works. So Pascal's triangle, and hopefully remember how it's built. You just add the two terms above it. So here 1 plus 1 is 2. So this is 1, 3, 3, 1, and 1, 4, 6, 4, 1. Okay, and we notice some patterns which you probably would have seen before. And one of the patterns is that the first number and last number in each row is equal to 1, and the second number and second last number is always equal to the row number. This is row 4 because 0, 1, 2, 3, 4, and the second number is 4. Okay, and that second number corresponds to the power that we're taking of this binomial. Okay, so if I were to continue this down, okay, up to the nth row, I'd have, starting 1, and I know that the second number in that row is just going to be equal to n, whatever the power is that I'm taking. In other words, the nth row of Pascal's triangle. All right. Now, at this point, we don't know what all these other terms are going to be. We know the second last one will also be n, and then we've got a 1. But we're going to see that in our demonstration here, we're not going to care what these numbers actually are. This is really going to be the only important one that we're going to focus on. Now, for those of you taking data management, you may have already seen this, or you will be seeing it soon, that you will come up with formulas for all the terms in any row of Pascal's triangle. All right? So let's expand this. Obviously, we're not, and this is why this is more of a demonstration, not really a proof, because we're not really going to write out all the terms, okay? But I think it'll be a good demonstration as to why this works. So limit as h approaches 0, and let's remember how this expansion works. All right, So these numbers in the row give us the coefficients, and then the variable terms are given by the different powers of x and h. Okay, so my first coefficient is 1, and I start off with the highest power of x, so x to the n, okay, times h to the 0, the lowest power of h. But of course, h to the 0 is 1, so we don't bother writing it. All right, so next one is, well, we know the next coefficient is going to be the second term in the row, which we determined should be n. Okay, the power of x goes down by 1, so n minus 1, and the power of h goes up by 1, so from h to the 0 to h to the 1. Okay, now the next term, I don't know what this coefficient is. At least at this point here, I'll assume we haven't seen the formula for the terms in the expansion. So I'm just going to call this a subscript n minus 2. It's just representing some coefficient. I don't know what it is, but we're going to see that it won't matter. It's just some number. So again, what happens? The power of x goes down by 1, so this becomes n minus 2, and the power of h goes up by 1, so it becomes x squared. And this keeps going, okay, all the way till I reach, well, I'll write out the second last term. So the second last term, I do know the coefficient's going to be n, okay, times x, okay, to the 1, and then h to the n minus 1, okay, and then lastly, we know the coefficient's going to be equal to 1, and x is going to be to the power of 0, so x to the 0 is just 1, and h is going to be to the power of n, okay? So this is what the expansion of x plus h to the n would look like, okay? It's got lots of terms. We haven't written all the terms, but this is going to be the format. And then, of course, we have the original minus x to the n, and all of this over h. And you may already see what's going on here, because this x to the n in the expansion, hey, subtracts out with the x to the n in my equation. And if you look at all the terms that are left over, sorry, this was supposed to be h to the n, missed the exponent there. Okay, if you look at all the terms that are left, what do they all have in common? They all have at least one factor of h. So I'm going to factor that out. Okay, so the first one has just one factor of h. So I'm just left with n times x to the n minus 1. And again, I'm hoping some of you are seeing where this is going. And the next term, okay, we just called this a n minus 2. It's just some number times x to the n minus 2. And here now I've removed one of the h's. So I'm just left with 1h. Okay, and all of these other terms are still going to have h's in them, because the next one will be just h squared, h cubed. Okay, I get to this one here, n, x, h to the, well, I'm just subtracting another h, so there's going to be n minus 2. And then lastly here, we have, I'm taking out one of the h's, so I'm left with h to the n minus 1. Okay, and now we have exactly what we were hoping for. This h here reduces with that h there, and now I'm just left with something for which I could take the limit. Okay, so I'll just write it out quickly here. And I see that h is approaching 0. This term has no h in it. It's unaffected by the fact that h is approaching 0. But each of the other terms left in this expansion all have a factor of h. So regardless of what these numbers are in front, this portion is always approaching 0. So all these terms just approach 0. And what are we left with? N times x to the n minus 1, which is exactly what we had conjectured. Okay, so while this is not a perfect proof, because we don't quite have the notation to represent this whole expansion that we wrote out, okay, it's actually very close to the actual proof. Again, all we're missing is some notation. So here we're seeing a really great application of Pascal's triangle. Okay, so let's keep in mind that this was predicated on the fact that n was a positive integer exponent. Okay, we couldn't have been able to expand this if x was, if n was 1/2 or 3/2 or 7/3. Okay, so this really only is a proof for x to a positive integer exponent. So you'll just have to take it on, my word that this rule actually does work for all n values. All right. So let's just recap what we have now. Okay. We now have a rule for constants. Okay. So derivative of any constant is always going to be equal to 0. You can easily prove that using the definition of the derivative, or you can just realize that this just represents a horizontal line, so the rate of change is always the same. Okay, we have that the derivative of any power of x can be found easily, so nx to the n minus 1. We have that the derivative of a constant times a function is just the same as multiplying that constant to the derivative of the function. All right. This was the one I didn't prove, so you should be proving that on the other sheet. And lastly, we have that the derivative of a sum or difference, okay, and we proved the sum was just equal to the derivative of the individual functions, and then you can add those together. Okay, and with these rules here, this means that we can determine the derivative of any polynomial function and any combination of powers of x. So not just positive integer powers, but with this one here, any powers of x that we're multiplying by constants, that we're adding and subtracting. All right. So I'm just going to do a couple of examples here, so you see how this works. So here I have a polynomial. So if I want to find, so since I've defined y as being this function, I'll use the prime notation. It'll be a little simpler. Now what we're really going to be doing here is splitting this up into 4 different derivatives. Okay, we're going to be using this constant multiple rule for 3 times x cubed. Okay, and then we're going to be using the derivative constant rule here. However, it's not really necessary to write out all those steps. So the idea is to start getting used to, doing this as much as possible in one step. Okay, I'll actually do it in 2 steps for this first one. So let's take a look here. I know that I can separate these out. I don't have to write that out. So if I want to take the derivative now of 3x cubed, 3 is just a constant. So this derivative is going to be 3 times the derivative of x cubed. And the derivative of x cubed, now we're going to apply the thing we just proved, is just 3x squared. Okay, minus. This is just a power of x. What's the derivative of x squared? 2x. Okay. This is 4 times the derivative of x. The derivative of x is just equal to 1. So this is plus 4. And then the derivative of 12 is just 0. Normally we don't write it, but technically you are taking the derivative of that part of the function, and it's just equal to 0. So your final answer is just 9x squared minus 2x plus 4. Okay, so not surprisingly, the derivative of a cubic function is a quadratic. Okay, and eventually you should be able to go straight from this line to that line. Okay, for now I just added one extra step just as we're getting used to taking these derivatives. All right, let's move on to the second one. So here I've got this function and I'm looking for the derivative. So again, I'll use the prime notation, but I think it's going to be much easier to find the derivative if I change this into a power function. So the first thing I'm going to do is I'm going to write this as a power of x. So this is just x to the power of 4, and cube root is just 1/3, so the power of 4 over 3. All right, and so now when I take the derivative of that, the exponent becomes the coefficient, and I just have to take the original exponent and subtract 1. So in other words, subtract 3 over 3. So what are we left with? 4/3 times x to the, well, this is just going to be 1/3. Okay, and if I wanted to, I could of course write this in a nicer way. This is 4 times the cube root of x over 3. All right, now this is where things get a little dicey, because one of the things we realized that as much as we would have liked there to be an easy quotient rule, there wasn't one. So at first glance, this looks as though it can't be done with what we know. But hey, we can just distribute this division to each of these terms. Let's rewrite this as, okay, normally I wouldn't write this step, but let me just be really clear as to what I'm doing. So I'm distributing the x squared to the first one, and this is x to the 1/2 over x squared, and I see that I can write this in a nicer form that allows me to use the properties we just found. So this is just x, and this is just, well, 1/2 minus 2 is x to the negative 3/2. Okay, and now I can take the derivative of this function pretty easily. Okay, so y prime is equal to, so again, I could split this up into the two simpler derivatives and then subtract that. So the derivative of x is just 1 minus, and now here, let me take the derivative of this here. So again, the old exponent becomes my coefficient, and then I'm just going to take this exponent and subtract 1. So negative 3 over 2 minus 2 over 2 is negative 5 over 2. Okay, so this is just 1 plus 3/2 x to the negative 5 over 2. Okay, and you're going to see that for this first unit, I'm actually going to give us a little break. I'm not going to be picky about writing this out in a more formal way. I'll actually accept this as an answer, but of course, you know, technically we shouldn't have a negative exponent, so 1 plus 3 over 2 times, you know, and I guess we could write this as the square root of x to the 5th. Okay, it's maybe the nicest way to write it. All right, so just to recap, we used our good old friend Pascal's triangle to come up with a way to prove this power rule, at least for positive integer exponents. And now, with the properties that we've established, we can come up with easy derivatives without having to use a limit definition of any polynomial and any combination of powers of x, even if they're not positive integers. Okay, that's it for this one.